Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, good afternoon. Welcome, everybody. Thanks for joining us here. I am not Dan Fay. Dan is the host of today's lecture, and he had to run away for a family situation, not an emergency, but had to take care of some family business. My name's Alex Wade. I am here with External Research, and it is my pleasure to welcome today David Anderson. David received his PhD in computer science from the University of Wisconsin in '85. He's taught in the computer science department at Berkeley, UC Berkeley, worked at several startups, and then has been back at UC Berkeley as a research scientist since then. His work focuses on citizen cyber science, using the internet to involve the global public in scientific research. And he's currently lead of the BOINC project, the Berkeley Open Infrastructure for Network Computing, which develops widely used middleware for volunteer computing. And he's also involved in creating new technology for distributed thinking and web-based education. I'd like you to join me all in welcoming David Anderson to Microsoft Research today.
Thanks very much, Alex. So today I'm going to talk about the field of volunteer computing, where we're at today, where we're going in the next couple of years, and at the end I'll say a couple of words about my new interest in involving people themselves rather than their computers to do science. This slide shows the history of volunteer computing. Volunteer computing is a form of scientific computing where the resources, the processing power is volunteered by computer owners. And the projects that got this started in 1996 were kind of proof of concept things, looking for prime numbers and breaking crypto systems. SETI at home and folding at home were the first ones that were doing kind of new science or real science, and they also added graphics to show people what was going on in their computer, and that seemed to make a big difference. They got really big. These early projects all developed their own infrastructure software, the software that manages the distribution of jobs and acts like a screensaver and things like that. And that turned out to actually be a lot of work. So a bunch of groups came up with the idea of making platforms to facilitate this sort of thing. The first several of these were commercial. People tried to figure out how to make money off of volunteer computing. None of them succeeded. In 2002, I started to work on the BOINC project, which is an open source middleware platform for volunteer computing. And that led to a proliferation of volunteer computing projects starting in about 2004. So currently there are maybe 40 or 50 fairly large-scale volunteer computing projects. It's still kind of dominated by SETI at home and folding at home, but there are a bunch of other fairly large ones these days. The applications that these projects do and the kind of science that they're doing runs the gamut of across pretty much all areas of computational science. A lot of them are involved with computational biology, things involving protein folding, which is sort of simulating how proteins develop out of gene sequences, or virtual drug design, which is figuring out how molecules bind with proteins. A lot of this has applications to very practical problems like developing vaccines or drugs for human diseases. There are projects studying, for example, how malaria spreads, improving models of the spread of diseases to figure out how we can spend prevention dollars optimally. Some volunteer computing projects, well, there's one from CERN that has run simulations of the Large Hadron Collider, both the accelerator part of it and simulating collisions in the detectors. There are some projects that study climate change and global warming. A number of projects involving different parts of astronomy. SETI, Einstein at Home is looking for gravitational waves using the new LIGO detector. Some projects doing mathematics, various brute force searches. BOINC can also be used to not necessarily do large-scale computing, but just as a way of deploying a program on a lot of computers. So there's an interesting project called the Quake Catcher Network from Stanford, which uses the accelerometers in laptop computers as pieces of a distributed seismograph. And you can actually detect earthquakes earlier than you could otherwise because of the proximity of computers to the earthquake. And I should point out that almost all of these applications were not developed for volunteer computing. There were programs that the scientists were already using, and in some cases they had to do some work to get them to run on consumer platforms. So, for example, the climate study projects had to take these climate models, which are huge multi-million line Fortran programs that had previously only run in supercomputers, and try to get them to compile for Windows, and that sometimes takes a certain amount of work. Also, all of the applications are what are called bag of task applications. They involve a bunch of independent jobs that don't communicate with each other. Though there is also the possibility of running MPI type programs on a restricted set of computers. Most of the applications are more compute intensive than data intensive, though as consumer networks become faster, that limitation is disappearing. So volunteer computing is a way to get a lot of computing cycles. And the way that the units that people talk about computing power in these days, the main units are teraflops and petaflops, which are thousands of teraflops. The first computation to exceed the petaflop barrier was Folding at Home, which is a volunteer computing project. That was reached last fall, and it happened many months before the first supercomputer achieved a petaflop throughput. The union of projects that use BOINC, I should say that Folding at Home is one of the early projects that developed their own infrastructure software. The totality of BOINC-based projects exceeded the petaflop barrier earlier this year, and it's currently averaging 1.2 petaflops. And I should probably make a couple of comments here. The Folding at Home's computing power, the bulk of it currently actually comes from Sony PlayStation 3s. The cell processor in that does about 100 gigaflops, so they get a lot of power from that. And recently they also have developed a version of their app that runs on NVIDIA GPUs. And with a fairly small number of computers, that is now providing 40% of their total power. BOINC is still almost entirely CPU-based. There are about 570,000 computers running BOINC around the world. The majority of those are Windows, so the vast majority of scientific computing done on Windows is done using volunteer computing right now. So in addition to being a source of a lot of flops, volunteer computing is a really good deal. If you work out the expense of getting 1 teraflop per second of computing power over an entire year, and you look at different approaches, the approximate numbers are like this. If you build a cluster yourself and you buy the hardware and the networking equipment, and you pay the electricity bills and you pay sysadmins to keep the thing running, it ends up being about $124,000 a year per teraflop. Cloud computing is another way to get cycles. The Amazon Elastic Computing Cloud, that teraflop year would cost you $1.75 million. If you look at the top, at the 10 largest BOINC projects, their expenses are really dominated by hiring a sysadmin to keep a server running. It's a BOINC project has a server which is typically a Linux box or a few Linux boxes. The hardware costs are almost nothing, and the cost per teraflop year is about $2,000.
How much electricity are the people at home spending beyond what they would if they weren't running these?
That's a difficult question to answer. In many cases, the computation is done while the computer is on anyway.
It might be running a little hot.
Yeah, it'll use about 30 more watts if it's doing a floating point intensive computation. There's no doubt that a large amount of that electricity cost, which is lumped into the cluster, is somebody's paying it. It's just not the scientist. It's being spread out among a lot of computer owners. So the real goals of volunteer computing, it's not to set records or to break barriers. It's to facilitate new science and to, in particular, to allow science to be done that wouldn't happen otherwise because people couldn't afford it. If you look at the top 500 supercomputers, historically, most of the top ones are owned by defense labs and they're used for nuclear weapons research. Volunteer computing is a way to get a lot of cycles if you're working in an area that's underfunded, like you're doing SETI or you're studying diseases like malaria that don't have a lot of money behind them, or if you're a scientist working in a country that doesn't have much computing infrastructure, or you're doing science that's speculative and unpopular in the current political environment of your area. Volunteer computing gives power to scientists who can explain their research to the general public and convince the public that it's worth this investment in their electrical bill to help the scientist. And conversely, what we're trying to do is to create an environment where computer owners have a wide choice of things that they can participate in, and they will try to make an informed decision by actually going out and learning about the science that these various projects are doing, and that process will increase their awareness of scientific research and their interest in it. So that's the idea. I wouldn't say we've made really good progress. The numbers that we have right now, there's roughly 500,000 people participating in volunteer computing, about 1 million computers, but that's out of that's maybe 0.1% of the 1 billion or so internet-connected PCs right now. And on the science side, 50 or so projects is a tiny fraction of the scientists who could potentially benefit from volunteer computing. So let me say a little bit about about reaching the exaflop barrier, which is 1,000 petaflops. And this is something that if you think about building an exaflop supercomputer in the traditional sense of having a bunch of hardware in a room, it's not really feasible. The economics, for maybe 10 or 15 years, it's going to take too much power and too much money. But we can potentially reach the exaflop barrier using volunteer computing a lot sooner than that. To start to think about this, we need to consider not just CPUs, but other kinds of computing devices. And I'm going to go through a few of these and talk about their potential to supply computing power. So for each one of these different kinds of devices, we need to think about its performance and how fast the performance is going to change over time, how easy it is to program for scientists. The energy efficiency issues will become more and more important, and there's also pragmatic issues of deploying volunteer computing on these different kinds of devices, some of which are controlled by single companies. So CPUs will continue to be an important part of the cycle pool for a while. Their contribution will come more and more from multiple cores, and the value of having an application that uses a lot of cores versus trying to run a bunch of separate jobs on individual cores mean that using this power will require writing parallel apps. That'll become increasingly important. In addition, there's a lot of mechanisms being developed to save electricity, which mean that computers will shut down or go into low power modes, and their availability, the fraction of time that you can do computing on them is going to shrink. I mean, the model is definitely that the computing will happen while the user is at the computer in some zero priority mode that stays out of their way, as opposed to the old model where when your screensaver kicks in, that's when the computing starts. Moving from the current million or so PCs to tens of millions of PCs, it's going to take the help of somebody like Microsoft or a computer manufacturer or a media company. Basically, we currently have the market of, computer enthusiasts pretty much saturated with volunteer computing, but reaching just sort of the average person who uses the computer as an appliance, that's the hard part. The next type of device, which is actually, I think, the most interesting, is GPUs. This picture shows why GPUs have a performance advantage. They don't have to devote a whole lot of transistors to caching and creating the illusion of random access main memory at processor speed. So, for example, the current NVIDIA chip does about 500 gigaflops, half a teraflop. That's maybe 50 or 100 times faster than the CPU on a typical PC that it's in. Programming GPUs to do scientific programming has become easier recently with the introduction of CUDA, NVIDIA's C-based environment for GPU programming, and Apple has announced something called OpenCL that seems to have the same goals. So we could get an exaflop, 10 to the 18th flops per second, if we had 4 million GPUs and each one did a teraflop, which is going to be the case a year or two from now, and we had 25% availability. In other words, they're running a quarter of the time. There is an exaflop, and that could conceivably happen in 3 or 4 years. Another type of resource is video game consoles, which are becoming faster as people want to have more realistic games and so forth. These could potentially provide non-trivial computing power, but they're inconvenient for a couple of reasons. They can be hard to program, in the case of the Sony PlayStation 3, and in general they tend to have closed environments that are hard to get your program deployed on. So my crude calculation is that they could potentially give us a quarter of an exaflop in a few years. Another kind of device that people have been thinking about recently because of energy efficiency issues is mobile devices. things like cell phones and PDAs, media players, the Amazon Kindle. Currently, these are sort of discrete categories, but internally they're converging to the same sort of hardware. And the processors in these are designed for low energy consumption. So in terms of flops per watt, these are the best thing going. And I should say that we're thinking about, one can consider using these while they're recharging. You wouldn't want to have your battery being sapped by running a scientific program while the thing is in your pocket. The software environment is problematic. Things like Google's Android, the proposed open source environment for cell phones, is a possibility, though currently that requires doing everything in Java. There's a lot of these. There's currently over 3 billion cell phones, and it'll go up to 5 billion pretty soon. But they're so slow that actually, even if you got hold of a lot of them, it's a lot less computing than you could get out of GPUs. So it's an interesting idea, but I think that GPUs are more important. Similarly, appliances like home media players are moving to a full-featured PC inside the box. So cable set-top boxes and Blu-ray players are typical of this category. The software environment is converging to a Java-based platform. So again, we have the problem of not being able to compile your Fortran program for it. So they could potentially give us a fraction of an exaflop. Okay, so that's the summary of why I think volunteer computing is the quickest path to reaching this exaflop milestone. Let me talk a little bit about the BOINC project, which I lead at Berkeley, which essentially provides an operating system for doing volunteer computing. We're a little tiny project, me and 1.5 other programmers. Most of what we do is developing technology. We write software. And to fill a vacuum, we also try to enable a variety of online communities related to volunteer computing. So we run a bunch of email lists and message boards, and for people who do things like writing translations or providing customer service, customer support for users, doing testing. The task of testing our software on all the popular platforms in the world is way more than we can do ourselves, so we have a lot of volunteers to do it. Let me just kind of quickly describe what BOINC is, what the software itself is, and some of our development efforts these days. There's two halves to the BOINC software: the server part and the client part. The server part consists of a job processing mechanism, and the key component here is a scheduler. It's basically a batch queuing system that has to have extremely high capacity. Many of these projects have hundreds of thousands of clients, and they need to be able to handle hundreds of requests per second and issue them a single job or maybe several jobs. So out of a database that at a given point may have 1 million or so jobs in it, the key aspect of the architecture is that the schedulers are insulated from the database, and that there's a cache of jobs in shared memory which is replenished by a separate program, and the schedulers, instead of having to go to the database and find jobs that are appropriate for that particular client, can just look in the cache, and that works really well. The BOINC scheduler is able to dispatch in the order of 10 million jobs a day, which is very important. The other part of the BOINC server software is a whole bunch of PHP code that provides a website for the volunteer computing project. And this is real important because one of the things that brings people in to volunteer their computer and that keeps them going year after year are competition mechanisms and community features of various sorts. So people like to keep track of how much work their computer has done, compete with other people, form teams, compete among teams, talk with other people about the science that's going on, and all sorts of things. And these are really critical functions. We've tried to make it really easy to set up a computing project using BOINC. So you can either set up a Linux box and install the BOINC software on it and port your application to our API, which is very easy. And in a day or so, you can have a project up and running. Even easier than that, we've created a VMware virtual machine image that has all the BOINC software already there and everything that it depends on, like the proper versions of MySQL and PHP and so forth. And you can run that virtual machine on any computer you want and get things going even faster. If you want to avoid even worrying about hardware, it's generally the server that you run this stuff on, you want it to be highly available and scalable and so forth. We're working on developing a virtual machine image for the Amazon Elastic Computing Cloud so that you won't even have to worry about hardware anymore. So we're trying to really reduce the barriers to entry for volunteer computing as low as we possibly can. The client software, well, first of all, it runs on all popular computing platforms. It's really designed so that a non-technical computer owner can install it with one click, not do any configuration at all, and have it work indefinitely after that with no intervention from the user. There's also, of course, a big category of users who want to configure things and who want to have a lot of knobs to turn and so forth. The actual internal structure of the software is a bit involved. It looks to the user as a single entity, but the programs that make up the client software, this picture shows what they are. The central program is what we call the core client. It's in charge of doing all network communications, talking to servers, getting jobs, downloading files. It's in charge of doing CPU scheduling, deciding when to run applications. The different pieces of the GUI, well, there's what we call the BOINC manager, which shows you kind of a spreadsheet style picture of what's going on. And if you want, there's also a screensaver. Both of these can run application graphics. So an application actually consists of two parts: the part that does the scientific computing, and if it wants, it can have a separate piece that does graphics and talks through shared memory so that you can see the current state of the computation. The interfaces between these, the GUI controls the core client through RPCs over a TCP connection. So, in fact, you can use the GUI to control clients on remote hosts. Now, the bigger picture, if you install the BOINC client software on a PC, initially it doesn't do anything. You have to then do what we call attach the client to whatever set of projects you want. So, like I say, there's on the order of 50 projects out there, and we want people to go out and read their websites, learn the science that they're doing, decide which ones they think are important. And then you can attach your computer to any subset of the projects. An attachment has an associated weight, which says how much of your resources you want to go to the different projects. So you could spend 80% of your time studying the climate and 20% doing some sort of biomedical stuff or whatever you want. The key idea is that these projects are completely independent of each other. There's no central BOINC authority. There's not even a official listing of all these projects anywhere. Each one has its own server. They're identified simply by the URL of their website. Now, the goal of this model is to promote kind of an ecosystem where new projects are constantly arising and disappearing, and volunteers are constantly learning about new projects and assessing their priorities. In practice, this is kind of difficult because the only way that people have for finding out about new projects is by Googling or word of mouth or something like that. We've developed a framework that supports intermediate websites called account managers. So the idea is that an account manager provides sort of one-stop shopping for volunteer computing. It's a website where you can go and look at all the available projects, summarized in some way, and their research described. And you can attach to them just by clicking checkboxes, as opposed to having to go out and survey a whole bunch of separate websites. To make this possible, the BOINC server software provides a set of web services so that account managers can create accounts on the different projects and look up stuff, manipulate stuff. There's currently 2 of these. One is called Grid Republic, the other is called the BOINC Account Manager. Some of the sort of technical work we've been doing recently, as it's become clear that supporting GPUs is very important, and also supporting multi-thread applications that can use multiple cores is important. We've had to kind of revamp the internal architecture of BOINC. Originally, the idea is that a client talks to a server and it tells the server what its platform is, or it can actually give it a list of platforms, so it may be able to run both Win64 and Win32 applications. The server has a bunch of jobs. Each job is associated with an application, not with a platform or a version or anything like that. The server goes through and finds the whatever it thinks that the best platform would be and sends the client that particular application. Well, with the advent of multi-threaded and coprocessor applications, we needed to generalize this. So in the current architecture, a given platform, like Win32, may have a whole set of different application versions that run on that platform. So there could be one which is optimized for sequential processing, one that's a multi-core version, one that uses a CUDA GPU, maybe another one that uses both multi-core and CUDA. Now, there's the problem, of course, is figuring out for a given client which of these different alternative application versions is best. And instead of embodying that intelligence in BOINC itself, we came up with an architecture where the project supplies a sort of a plug-in function that goes into the scheduler, which takes as input a description of that particular host, its CPUs, its coprocessors, everything else about its hardware, and goes through these different available versions, and for each one decides how many cores will that application be able to use in that machine, how many coprocessor instances, how many flops does it expect the application to get running in that machine. And then we can use that information, first of all, to pick whatever the best version is, and secondly, to get an estimate for how long the job is going to take to run there, which is critical for the to make a good scheduling decision. Just kind of jumping around here, another thing we've been working on is improving our replication algorithms. So one interesting thing about volunteer computing is you're using computers that are essentially anonymous, and you can't trust them. You can run a program on them, you get back an answer. You can't even be sure that what you get back is the result of running your program. There are a few bad apples who will intentionally send you back wrong stuff or the output of a previous run of the program or something like that. In addition, when you're dealing with this number of computers, a lot of them have hardware problems, especially those that are overclocked. They can get floating point errors that don't crash the system, but they give you bad answers for a scientific program. So one way to deal with this is to do replicated computing, take the same job, run on two different computers, compare the answer, and accept it only if they're the same. It's actually a bit trickier than that because different computers actually don't do floating point math the same, and if you run the same program on an Intel and an AMD processor, you can get back wildly different answers, especially for unstable computations. Anyway, so replication, we've worked it out, and it's a way to increase the trust in your result to whatever level you want, but it wastes computing power. So one thing we're working on right now is a more intelligent system where we do replication only some of the time. And if we're sending jobs to a host that has built up trust, then we, with a certain probability, don't replicate that particular job. So the policy that we're looking at right now maintains an estimate of the kind of the error rate for a host. And if we're sending a job to a host whose error rate is above that, we always replicate. Otherwise, we replicate with a probability proportional to the error rate. So the idea is a host earns a certain good reputation, and after that we don't always replicate, but every now and then we mix in a replication. It's a little bit unclear whether there are counter strategies that would defeat this scheme, and if anybody is into this kind of stuff, I would enjoy talking to you. BOINC involves some very intricate scheduling policies. There's actually kind of two interacting schedulers in BOINC, one that runs in the client and the other running on the server. The client has to decide when to get new work and what project to get it from and how much to ask for. And at any given point, it has to decide how to schedule the CPUs among existing jobs. This can be kind of tricky when you have computers that are disconnected from the network some of the time. You need to prefetch enough work to keep them busy while they're not connected. If you fetch too much work, you can miss deadlines. You can in the presence of replication, you can cause other replicas to sort of get delayed for a long time until you can validate them. And similarly, there are a bunch of the server scheduling problem can be very hard. Until now, we've mostly experimented with scheduling policies by, coming up with something that sounded feasible and deploying it on a running project. The problem with this is that if you make mistakes, you can waste a lot of computing time and get a lot of people angry at you. And the other problem is that there's a lot of factors going on at once, and you can't really be sure that the result you see is because of the change that you made. So we're developing two simulators, essentially one to study the client and one to study the server. So for example, the server simulator consists of a program that emulates a huge number, like hundreds of thousands or millions of clients, and it models things like their error rate, the churn rate, the process of people joining and leaving the project, the distribution of speeds of the computers and so forth. And that actually plugs into a real BOINC server. So to maximize the accuracy of the simulation, we don't simulate the server. We use a real live server with the actual programs and a database behind it, and that actually runs fast enough that you can simulate it about 100 times real time. We also do a lot of work on the community and competition, the volunteer-facing features of BOINC. And in the past year, we've added a bunch of features that sort of emulate what you might find on a typical social networking website. The ability for people to make lists of friends and have pictures of each other and send messages around. A lot of stuff related to teams. Teams turn out to be a surprisingly powerful mechanism to motivate people in volunteer computing. And we've sort of souped up the idea of teams so that there can be structure within a team. You can have administrators, kind of lieutenants, as well as the master of the team, the ability for a team to have its own private message boards and things like that. And we're also figuring out ways to introduce volunteer computing into the big social networking sites, like having applications Facebook applications, so that people can see when somebody has joined a new volunteer computing project, or when somebody's total amount of credit has passed a milestone. That'll show up on their list of events. And to make it, yeah.
Can you describe how a team knows that it's beaten another team?
Well, there's elaborate features for showing lists of teams, and either their total credit or their recent average credit. You can filter teams by only certain countries, or by company teams and university teams. You can group things in various ways. And the other general mechanism is that, in addition, we don't really want people to think in terms of individual projects. We want to think of their totals across all the BOINC projects. So we have a fairly elaborate system where the projects export all of their credit statistics in XML files, and these third-party websites aggregate that data and show various forms of competition and leaderboards summed over all the BOINC projects. So, like I say, currently there are about 50 BOINC-based projects. This number is embarrassingly small. I hope that there would be 1,000 by this point. One reason for this is that even though we've made it super easy to create a BOINC project, it's still beyond the capabilities of the average computational scientist. People who do scientific computing are not computer whizzes. They're not sysadmins. In many cases, they're not actually programmers. And the idea of a volunteer computing project being operated by a single scientist or a single research group, I think we've sort of hit the limit of how far that model will go, because there's not that many research groups that have the resources to do something like this. There's a bunch of other organizational models. My favorite is what I call the campus level meta project. So the idea, and this is being deployed at the University of Houston, hopefully that'll inspire other people to do it, is a volunteer computing project that's operated at the level of a university. It handles applications from all of the scientists at that university. The servers are operated by sort of a central group, and the website and so forth. And it's promoted, well, first of all, the computers of the university itself, like the lab machines and so forth, would be configured to run that project, to support the university's own research. It would be promoted to the university's students. So University of Houston, for example, has 30,000 undergrad and grad students, and hopefully a lot of those would want to support university research in their machines. It also has 400,000 alumni, and this is the interesting number. Alumni have school spirit that manifests itself in going to football games and sending in money every year. It seems like it would be pretty straightforward to get these people to run volunteer computing for the university on their computers. Most of them own computers. So I think that's kind of an ideal way to do things, and I'm trying to get some universities interested in that. There's a few other organizational models. There's a project called mindmodeling.org, which essentially is centered around a particular application. These are people who build giant Lisp programs that model the human brain in all of its different components. And there's one of these programs that's called ACT-R, and there's a lot of researchers that use this, and that community has have come together to create a volunteer computing project that just runs that one application, and any of those scientists can feed jobs into it. IBM World Community Grid is another meta project or an umbrella project operated by IBM more or less as a PR exercise, and it hosts a number of applications from a variety of universities all around the world. And there's a few other things going on. In Spain, there's a province called Extremadura where essentially all the universities and research labs have decided to form a volunteer computing project that spans all of them. Okay, let me kind of shift gears here and talk about my a recent interest of mine, which is related to volunteer computing in the sense that we're trying to use the public to help scientific research. The idea here is to use the people themselves and their intelligence, their cognitive abilities, their knowledge, rather than their computing power. So a couple of years I got involved in a project at the Space Sciences Lab where I worked called Stardust at Home that had to do with finding particles of interstellar dust in a chunk of aerogel, this very odd material that had been sent into space and had collected a certain amount of cometary and interstellar dust and was parachuted back to Earth. The problem was that nobody knew where the dust particles were or how many there were, and they didn't even really know exactly what they were going to look like. So it was impossible to. We thought about attacking this problem with computer vision, image processing, and it didn't work. So instead, we set up a system where we would train people on what we thought these dust tracks would look like. So they would look at microphotographs of this aerogel, actually not just single photographs, but sort of a stack of photographs at different focal planes. So there's a knob where you can kind of turn a focus knob, and what you expect to see is a little tunnel that goes through the aerogel and a little cave down at the end. And you can't actually see the dust particle, but you can sort of tell where it is. And this was wildly successful. We got 23,000 volunteers who, on average, looked at 1,600 of these focus movies. Each one, takes maybe 30 or 60 seconds to look at, so they contributed a lot of time to that. There's a lot of enthusiasm. And we were able to calibrate exactly how well they were doing by introducing a certain random fraction of jobs that we had synthetically created. So either images that we knew didn't have a dust particle or images where we had kind of photoshopped in a dust particle with a certain size and orientation. So 20% of the jobs are these calibration jobs, and we were able to really quantify how well the volunteers were performing, which in the end turned out to be much better than individuals or graduate students could do. And there have been a few other of these projects, which I know my word for it is distributed thinking. Some people call it crowdsourcing. There's a project called Galaxy Zoo, where people look at deep space images and identify different types of galaxies. One interesting one from the University of Washington is called Fold It, and the goal here is to take a complex protein molecule and sort of fiddle around with it to reduce its potential energy. So this is what it looks like. It kind of shows you the places in the molecule where atoms are, where there's an empty space that needs to be filled in. That's the yellow balloons, or where atoms are too close together. Those are the red balloons. And you can kind of grab pieces and try to reduce the energy. And this is Folded is deployed as a multiplayer online game, so you can see a bunch of other people who are fiddling with the same molecule at the same time and sort of race with them to try to get the energy down. This task of reducing finding the low energy state of complex molecules turns out to be one of these things where some humans can do better than computers. So I started this project about 6 months ago I guess I like to write middleware, so I decided to write a middleware platform for distributed thinking to make it easy for scientists to make new projects like Stardust at Home and Fold It. And probably the central part of BOSA, that's the system I'm working on, is support for learning about your volunteer population. Basically figuring out who the savants are. There's going to be some fraction of volunteers who are so bad at the task that the best you can do is to ignore their contributions, and probably a few people who actually try to undermine your experiment. And the other thing I'm working on these days is a platform to make it easy to teach people in the context of distributed thinking and volunteer computing. Both of these areas have the property that you have this giant pool of volunteers, hundreds of thousands or millions of people from all over the world, all different ages, education levels, interests, backgrounds, and so forth. So extremely diverse. And you have more or less a steady flux of new volunteers, typically several hundred or maybe 1,000 new volunteers every day. And both for distributed thinking and volunteer computing, it's useful to try to teach these people something. Either teach them about the science that you're doing to get them more involved, or in the case of distributed thinking, to train them to do one of these applications that can actually be require a lot of knowledge, like fiddling with proteins. So you have this great diversity of the student population, and because you have a steady flux of students, there's the opportunity to actually create experiments. So let's say you have alternative lessons that teach a given concept. You could set up an experiment that runs these two lessons side by side, and has an exercise after that. And at the end of a day or two, you would have collected enough data to give you some statistically significant information about which of those lessons is better, or maybe one of the lessons works well for some subset of your population, like the older males or something like that. So that's the basic idea of this other system I'm working on called BOLT. Makes it easy to set up experiments and to have training that constantly evolves to get to teach more and more effectively, and can also be adaptive. Okay, so I guess that's I've reached the end here. So volunteer computing has done some impressive things in the past year. This petaflop barrier, the possibility of moving towards exaflop. But as far as I'm concerned, it's really just barely achieving the tiniest part of its potential, and both in terms of reaching a bigger volunteer population by 1 or 2 orders of magnitude and bringing in more scientists. Volunteer computing has not been embraced by the high-performance computing community or even the computer science community. You can go to the supercomputing conference and you will not hear one single reference to volunteer computing, unless I happen to be giving a talk there, which is rare. This idea of distributed thinking, I think, is real interesting, and it is at extreme infancy. I think we need to get scientists thinking about how they could potentially use that, and these two things can actually potentially link together. You can imagine workflows where distributed thinking processes data in some way that then feeds into a computing system, possibly a volunteer computing system. So if anybody is interested in either of these things, here's my email address. I'm real eager to think about starting new projects or to do research in either one of these things. So thank you very much, and I can answer any questions that anybody might have.
I have a question. Are there any significant results of the projects that used actually volunteering computing? I mean, I have some computation to make. I can't afford a cluster on myself, and I decide to go for volunteering computing. Are there, from the current project that are right now running on volunteering computing on BOINC, are there any significant results, things that they could actually achieve using this volunteering?
Yeah, a lot of them. Volunteer computing has an image problem, which is that most people think of it and most people equate it with SETI at home. And they say, SETI at home hasn't found ET, therefore volunteer computing is scientifically worthless. So to try to combat that, I assembled a list of the publications of all the projects that use BOINC, results that were possible only because of volunteer computing. And there's a goodly number. There's probably 4 or 5 papers in Nature and Science and PNAS, and a total of 50 or so papers. Folding at Home has a huge number of papers, all of which were enabled by volunteer computing. So there hasn't been the one big discovery. Nobody's discovered the cure for cancer or extraterrestrial life so far, but there's a steady stream of kind of standard size scientific results. It's the same as any other computing resource. It's just cycles.
Has anyone done anything with Flash or one of the other kind of applications running in the web browser where people don't install anything? It's just while they're sitting at this web page, their local computers doing something useful?
Yeah, there have been a few efforts in that direction. There was a very early one using Java applets. Like I say, most of the projects that use BOINC have some existing application, which is, if you're lucky, it's in C++. More often it's in Fortran. So pragmatically, that's sort of a limited approach. Yeah.
What's the primary programming model for BOINC? So if a scientist has like a Fortran program, do they have to adapt it to the BOINC infrastructure? Or there are different kinds of libraries available in the framework, in the BOINC framework that they could use? Or how does it work?
There's different options depending on how much work you want to do. The easiest option is to use what's called the wrapper, which where you don't have to change your program at all. In fact, you don't even have to have source code for it, and it runs kind of inside this wrapper that manages the communication with the BOINC client. If you want to, for a real application, typically you need to do checkpointing, and BOINC has a very small set of APIs that essentially communicate with the client to tell when the app should checkpoint and to acknowledge when the checkpoint is finished. If you want to do graphics, to have your app show something in a screensaver, there's some APIs for that. So, but they're all very easy to use, and there's Fortran as well as C, C++ bindings. Some people, you can also run Java applications under BOINC. Some people are doing that in Python.
Do you have some numbers regarding user usage patterns, like how often, like the growth rate in these years that like study at home has been used, and like how often do users join and leave in the project, like how much of the user they actually fake results and things like that?
Yeah, we have. We've collected there's a bunch of different usage data that one can imagine. There's the churn rate, the distribution of time that people actually participate. We studied that a little bit. There's a curve, which is pretty much what you would expect. We've studied the availability. So some people leave their computers on 24 hours a day, and BOINC is able to compute the whole time. Other people have BOINC set up to compute only when they're not using the computer, so there are these different pieces of time. We instrumented the BOINC kernel to collect all of that data, and we to log it, and we were able to send it back to the server. And we did that with SETI at Home, I think about 6 months ago. I generated usage data for about 100,000 computers and did some analysis of that. If you're interested in that, I'd be happy to supply any of that data. As far as the fraction of malicious or malfunctioning computers, we could probably reconstruct that, but we haven't done that so far.
Do you have a rough approximation of how much cheating is going on? Order of magnitude?
Order of magnitude is probably like 2 or 3 people out of a million. It's really small, but if the others learn that people are successfully cheating, they get demoralized, and it becomes known quickly. We added a lot of functionality in BOINC to detect and defeat cheating early on. And the pre-BOINC version of SETI at Home did not have any of those checks, and there was rampant cheating, which we had to deal with after the fact.
So with the BOSSA project, have you thought about, I was just looking at the wiki that you've got up about it, and it sounds like it's exclusively for sort of website level. You go to some website, you can then evaluate the photograph or do whatever. Have you thought about what it would mean to host that in a separate application, making that framework open so that if you've got, I don't know, Excel or whatever, that someone's already got a bunch of data in, and then you can have them use their big human brain and submit results over just the framework, like almost UI-less? I haven't thought of that, but it should be pretty easy to do.
If you have any ideas for for a good potential project, let's figure out how to do that.
Also been used at all in any psychological research?
BOSA hasn't actually been used for anything so far. It only started working about a month ago. The two pilot projects, just so you know, they're both image analysis. They're kind of interesting. One of them is looking for hominid fossils. So when people like Louis Leakey and so forth go out and try to find fossils in Africa, they do it by finding areas where erosion has exposed fossil-bearing earth, and then they just kind of walk around looking down at the ground really closely, and it's strewn with rocks and pebbles, and every now and then there'll be a tooth mixed in there, and you can't see it unless you like stare right at it. And these people become extremely good at recognizing bone fragments. But it's very hard to cover a lot of area that way. And when you do cover it, you trample stuff and you potentially break things. So this guy named Tim White at Berkeley, who's the new Leakey, we're working on a project where we'll get photographs of large areas of these fossil-bearing regions. The original plan was to have an unmanned airplane sort of crisscross the thing. I think in the end we're going to have a human-carried sort of rack that has a bunch of cameras on a kind of a frame and a GPS device, so you walk along and it automatically clicks. And then we'll have these people will look at these pictures on the web and try to find fossils. That's one. The other project involves annotating satellite images of Africa. There's this giant amount of data of satellite pictures, but there's no information about like where are the roads, where are the settlements, the crops, things like this. So we're setting up a project where people can annotate those images, and then scientists can learn something from them. It would be nice to think of a project that didn't involve images, something that involved some sort of AI knowledge kind of thing. Anything else? Thank you.
Thank you very much.